Hello everyone, I am A. Mani Raghavasri with registration number 22B0180502.
I'm Zinavya with registration number 22B01805551.
We are from Sri Vishnu Engineering College for Women, Autonomous,
We are going to conduct a video on semaphores.
under the guidance of Dr. M. Prasad, PhD, Associate Professor, Department of Computer Science and Engineering, SVCW, Bhimavaram. So first, let us see what our video consists of. Our video consists of introduction, about critical section, uses, operations, types, pros and cons, and finally the conclusion about semaphores. So first, let us see what is a semaphore. Semaphores are integer variables that are used to solve the critical section problem by using two atomic operations, wait and signal, which are used for process synchronization. So first, let us know what is a critical section problem. Critical section is the part of a program which tries to access shared resources. That resource may be any resource in the computer like a memory location, data structure, CPU or any IO device. The critical section cannot be executed by more than one process at the same time. Operating system faces difficulties in allowing and disallowing the processes from entering the critical section. The critical section problem is used to design a set of protocols which can ensure the race condition among the processes will never arise. So, to solve this critical section problem, semaphores are used. So now let us know why semaphores are used. Semaphores are typically used for the following purposes. Synchronization. Semaphores can be used to coordinate the execution of multiple processes or threads, ensuring they perform their task in a specific order. Deadlock avoidance. Semaphores can be employed to prevent or detect deadlock situations in concurrent systems by carefully managing resource access. Mutual exclusion. Binary semaphores are used to ensure that only one process or thread can access a critical section of your code at a time. Finally, semaphores are used to solve producer-consumer problem. Counting semaphores are used to manage the interaction between producer and consumer processes in a buffer, controlling the number of items in the buffer. Now, let us see what are the operations that can be performed on semaphores. There are only two operations performed on semaphores. They are wait operation and the second one is signal operation. First, let us know what is a wait operation. Wait operation is also called as P operation. It decreases the semaphore count. If the count is already zero, the calling process or the thread is blocked until the count becomes greater than zero. This is the pseudocode for the wait operation. As we have already seen that the wait operation will decrement the semaphore value by 1. So here we can see that there is a while loop. This is for if the semaphore value is already 0 or less than or equal to 0, it will tend to be in infinite loop. When the condition fails, the semaphore value will be decremented by 1. So first, if a process wants to execute, it is first tend to enter the wait method, where its semaphore value gets decremented. After the wait method, it will be gone to execution. This is the second operation which is performed on semaphores, which is signal operation. It is also known as V operation, which increases the semaphore count. If other processes or threads are waiting on the semaphore, it allows one of them to proceed. This is the pseudocode for signal operation. As we have already seen, signal operation will increment the semaphore value. The process, after completing its execution, will enter into the signal method and increments its semaphore value by 1. So, by entering into the wait method, its semaphore value will be decremented before execution. And after executing the process, its semaphore value will be incremented. So, by using the signal method and wait method, the processes can know whether the resources are free or allocated. So now let us see how many types of semaphores are there. There are two types of semaphores. The first type is binary semaphore and the second type is counting semaphore. So now let us see what is a binary semaphore briefly. A binary semaphore is a simple version of a semaphore which can have only two values, 0 and 1, which we have already known that the binary value is either 0 or 1. It is typically used for mutex, which means mutual exclusion, or critical section synchronization. It ensures that only one process or thread can access a shared resource at a time. Let us see what are the operations are allowed to perform on a binary semaphore. Previously, we have already seen that there are only two operations that can be performed on semaphores, wait method and signal method. Let us recall them that wait method will decrement the semaphore value and the signal method will increment the semaphore value. And as binary semaphore consists of only two values which are 0 and 1, if the binary value is 1 and if it prone to be in wait operation, its value will become 0. If the value of binary semaphore is 0 and it is in signal method, its value will be incremented and its value will be turned up into 1. Counting semaphore, another type of semaphores. A counting semaphore have an integer value greater than 1, which represents the number of available resources. It can be used for scenarios where multiple processes or threads can access a shared resource, but within a specified limit. Operations on counting semaphores. Here also there are only two operations which are performed on binary semaphores, which are wait operation and signal operations. We have already seen about wait and signal operations.
Now, I'm going to explain about the pros of semaphores. The first one is synchronization. Semaphores are effective for synchronizing access to shared resources in a multi-threaded or multi-process environment. This helping to prevent data races and ensuring the orderly access. And the next one is flexibility. Semaphores come in two main types, binary and counting, that provide the flexible. Binary semaphores are suitable for exclusive accesses, while counting semaphores can manage multiple resources. And moving to the other one, resource management. They can be used for resource allocation and protection, making it easier to control access to resources like memory, file handles, or hardware devices. And moving to the other one, priority control. Semaphores can be used to implement priority schemes, allowing specific threads or process to have higher access priority to resources when needed. And the final one, but not the least, deadlock avoidance. Deadlock avoidance is properly designed semaphore-based synchronization can help prevent deadlock situations by controlling resource accesses. As there are pros and there are also cons of semaphores. Now let's learn about the cons of semaphores. The first one is complexity. Semaphore-based synchronization can be complex and error-prone. Care must be taken to ensure the correct usage of semaphores to avoid the deadlocks or race conditions. And the next one is difficulty in debugging. Debugging issues related to semaphore misuse can be challenging as they often involve non-deterministic behavior and timing dependent problems. And moving to the other one is potential deadlocks. If semaphores are not used correctly, they can lead to deadlock situations where threads or process are unable to proceed. And moving to the other one, overhead. Semaphore operations, signal and wait have some overhead which can impact performance, especially in high contention scenarios. And moving to the final one, but not the least, lack of granularity. Semaphores are not as fine-grained as mutexes, making it challenging to protect specific data structures within a larger critical section. Semaphores are not limited to the operating systems, but they are also used in real-world scenarios. Now, let's see how the semaphores are used in real-world scenario. Semaphores are used in various real-world scenarios where synchronization and resource management are essential in concurrent programming and operating systems. Here are some real-world applications of semaphores. The first one is printers and spooling. In print spooling systems, semaphores can be used to control access to the printer. Only one job is allowed to print at a time, and semaphores ensure that multiple print jobs don't interfere with each other. And moving to the other one, database management system. Semaphores are employed to manage concurrent access to databases. They help control access to critical sections of the database, prevent data corruption, and maintain the data consistency. And moving to the other one, multi-threaded applications. In multi-threaded programs, semaphores can be used to coordinate and synchronize threads. For example, a thread pool may use semaphores to control the number of threads that can run concurrently. Moving to the other one, resource allocation and management. Semaphores are used in various scenarios like where multiple processes or threads need access to finite resources such as memory network connections or hardware devices. They ensure that resources are allocated and released safely. And moving to the other one, traffic signal control. In traffic signal control, computer simulations of traffic signal control systems, semaphores can be used to model and control the flow of traffic at intersections. Now moving to the other one, file system management. Operating systems are semaphores to manage the access to file systems, ensuring that multiple processes or users can access files without the conflicts. And moving to the final one, but not the least, parallel computing. Semaphores are applied in parallel computing environments to manage shared memory, coordination between parallel tasks, and synchronization. And these are now I'm going to conclude about this topic. Semaphores are key for resource synchronization in operating system and concurrent programming. They offer control but need careful handling to avoid issues like deadlocks. In real-world scenarios, they ensure orderly resource access. By using semaphores, process cannot get confusion whether the resources are allocated or free.
This is about the semaphores. Semaphores are not only used in the situations where we have told in this video, but they are used in the many other situations like in producer consumer's problem or in dining philosopher's problem. In very other situations, semaphores are used, like in the real world applications, in traffic signals and printing systems. So we can relate the semaphores topic to our real life so that we can easily understand about this. Okay, thank you for watching our video.